Hi, and welcome to our discussion of radioactive waste. We'll focus mainly here on describing how we get exposed to radioactive waste, um, the kind of hazards, the health hazards that are associated with it, and then a little bit about specific disposal sites. One interesting thing about the disposal of waste is there is really no place to dispose of it. It's a problem that's hanging around, lurking out there, but we don't really deal with it on a daily basis. Radioactive waste is made of material that is undergoing radioactive decay. Radioactive decay is a spontaneous chemical reaction. It is only predicted by statistics, so we don't know when it's going to happen for a particular element or a particular atom that has an isotope that will decay. But it will happen, and it will happen at different rates, and this is specific for different isotopes. In natural systems, we use this decay process to measure the rates or ages, or rates of geologic processes, and to measure the ages of rocks. However, in this case, we're really interested in radioactive waste. Usually it starts out as uranium-235 and ends up decaying to something like plutonium-239 in a spent fuel rod. That may be recycled in a breeder reactor. However, a lot of times, not every reactor is a breeder reactor, so that plutonium that's in the spent fuel rods, as well as cesium and strontium, are radioactive elements that aren't really useful once the rod is not generating a spontaneous reaction. So they have to be disposed of. Okay? On the right-hand side, we see the time in years and the fraction of original material remaining in a system. And so here we have 100%, 50%, 25%, right? And so on, all the way down to an eighth and a sixteenth of whatever we started with, which was 1. It could be 100 grams, it could be 1,000 grams, right? It doesn't matter. If we take a look at the half-life, every time we cut it in the volume in half, okay, we expend 1 half-life. So 1 half-life is a number of years to cut this material in half, for the decay process to half the amount of stuff we started with. So here at half, we're at 50%. For isotope A, it's 10 years, right? 10 years to get there. For isotope B, it's a short half-life. It's 1 year. Okay? Examples of half-lives, real half-lives, right? Strontium and cesium, down here at the bottom, are actually 30 years. So their curve is going to come all the way out to 30, way out here. That'll be for the first data point. And then it takes another 30 years way out here for them to decay even further. Right? At some point, we'll reduce the amount of fissionable material to where the radiation that's emitted, right, is relatively small. Right? But early on, after the first couple half-lives, there's still plenty of radiation in most systems. And you'll notice plutonium, okay, 24,000 year half-life. So we're dealing with material here that is highly radioactive. It has very long half-life. It has to be stored somewhere for a long time. This is one of the big problems, is a long half-life. The other issue with radiation is that we don't have any way to actually detect when we're exposed to ionizing radiation. Obviously, if we go out into the sun, we come back and we have a sunburn, right? But while you're exposed to the sun's rays, you often feel fine. It's not until that evening that you feel essentially the damage caused by radiation. And damage, especially from ionizing radiation, which penetrates through your skin, is cumulative. We assume that every X-ray that we get, every MRI, is going to cause some damage and increase our likelihood, okay, of developing cancer, for instance. Okay, so that's another problem with this material. There are 3 ways, or 3 types of radiation that we're dealing with here. There is alpha, beta, and gamma. Okay? Each of these types of radiation is a little bit different, and I have a kind of summary going on down here at the bottom. Okay? The most damaging radiation here is the alpha particle. Okay? It is the biggest. Okay? It should say fast moving. This says slow moving. It should be slow moving. Okay? And the alpha particle isn't able to penetrate even, see, paper right here or your skin. So the alpha particle is the most damaging, but it's the biggest, which means it doesn't really get through stuff very easily. So how do we get alpha particles to cause significant damage? We need to ingest them through inhalation. Okay? The beta particle, which is shown here, is a little bit more penetrating. It goes through paper and gets stopped by, say, aluminum foil. So, it's like you think about those jokes about people wearing aluminum foil on their heads, right? Well, that's great if you got alpha particles and you got beta particles coming at you. Aluminum foil is a good thing. If you're in a place with alpha radiation, though, you really need to worry about not wearing protective gear on your skin, but really having a respirator to filter out those particles. Okay, and then the most penetrating and sort of least damaging of the three in terms of creating damage to cells is going to be gamma radiation. Gamma radiation is not actually a particle. It's just a wave, short wave, high frequency, most energetic, and penetrating through things like concrete. And so often we need something that is lead lined to protect us from gamma radiation. The ionizing power here is the thing to pay attention to with regard to damage, right? So the penetrating power is low for alpha, but the ionizing power is high. And so ionizing power means the ability of these particles to bust electrons out of an electron shell, in a valence electron shell. If the ionizing power is high, the potential for damage done is very high as well. So gamma has sort of a lower ionizing potential and a lower ability than alpha or beta to cause damage. Okay? If we take a look at the amount of radiation that comes off certain medical devices and sort of the worldwide reactor fallout, chest x-rays, this is the stuff we get exposed to every day. We see that, radon, which is a gas that is formed in regions with a lot of granite, collects in your basement. Okay? It is exposed as a dosage of millirems per year. Now, a rem is a unit of measurement called radiation equivalent man. Okay? It is a dosage that measures or accounts for the amount of energy plus a factor that accounts for damage done, right? And so you'll notice a radon source is emitting 200 or so millirems per year. Cosmic rays and medical devices are only at 55 millirems. So those are supposed to be mainly supposed to be, pretty harmless. And then we see, consumer products, normal operating nuclear power plants with full shielding, the millirems are going way, way down. Okay, worldwide radioactive fallout, like that's something we're exposed to every day, right? In terms of the amount of fallout, pretty small. Radon, you want to avoid radon as much as possible. Chest X-ray, 10 to 39 millirems. Jet travel actually gets you some exposure to radiation, a small amount of exposure per year. Okay. Let's see, cooking, okay, with natural gas also gets you some minor amount of exposure. One of the problems that we have is with this is if we have increased risk of cancer on the y-axis here and radiation exposure on the x-axis, right? The idea is that we assume is that we follow path A. Right? Path A says I get exposure, I get increased risk of cancer. I get more exposure, I get a higher increase or more increased risk of cancer. The truth is we don't actually know what path is followed here. So it's possible that there's a limit, and that's what we call a threshold. That's path B, where nothing happens. We don't see any risk increase until we reach a radiation exposure limit. Let's say that exposure is like, I don't know, 10 x-rays or 100 x-rays or 1,000 chest x-rays, right? After 1,000 chest x-rays, we start to see the probability, okay, the risk of cancer increasing. Then there are exponential experiences here where we see a rapid increase, okay? So right away, exposure just jacks up your chances of cancer, or it could be very slow. And then as you get more radiation exposure, we see what we call an exponential increase in the possibility of having what we would consider a high dose experience. The high dose experience would be having cancer, right? That would be the thing that we would get from being exposed to radiation. And as I told you, it is assumed to be cumulative over your life. And that's because radiation, I mean, well, if there's enough radiation, it will actually kill cells. What it also has the power to do, you know, these beta particles, or particularly gamma radiation, is to pass through your skin and to damage the cell, but not to kill it, right? And so the damaged cell may reproduce, creating another damaged cell, and this is, you know, presumably how we're getting cancers. Okay? So what do we do with radioactive waste, right? Where does it come from? Well, we know that we have nuclear power plants because we've talked about renewable energy sources, alternative energy sources already. And the answer is we have no place to put any of it. Okay? There's one facility called the Waste Isolation Pilot Plant. This was developed by the military, the Department of Energy. It is designed to store radioactive material, what we call transuranic, so atomic numbers bigger than uranium, things like plutonium. And it is only designed for Department of Energy and military, or actually it's not even Department of Energy. It's not designed for commercial materials, but it's Department of Energy is, say, experimental reactors and military experiments. And so it takes in two kinds of waste. It's called WIP, right? WIP. It takes in high grade, okay, waste. So this is material that's been exposed to uranium, plutonium, isotopes. It would be high grade waste, and it comes in two varieties. One is going to be the material that is contact handled. That's the stuff that consists of clothes, shoes, any materials that were exposed to the waste or exposed to radiation. And then it also has the high grade material that's actually actively giving off a significant signal, and that stuff is handled remotely in the system. But the storage facility is actually underground in just outside of Carlsbad in New Mexico, and it is in a formation of salt. Okay? Radioactive waste, the storage of waste, is considered by a bunch of countries as being thought about, and in some cases facilities are being built. They're being built in things like granite, which has low permeability and low porosity, so it's a good place to put this material. This system is built in salt, which has low permeability and low porosity. Okay? One of the problems with salt is it will dissolve in a liquid. Okay? But the other advantage of putting it in salt, in particular the Salado formation here, which is in salt, one of the advantages is that salt has a very high melting point. So because this material is so energetic, there's a lot of heat given off. And if it was to escape, we wouldn't want it to be able to melt the surrounding rock through a runaway reaction, sort of generating enough heat melting shale or melting into the shale. We want it to not be able to essentially travel down because if it does travel down, it ends up where? It ends up mixed in with our groundwater. Here's an example of the WIPP site. Here's the Salado Formation. This is a thick salt. It's about 200 million years old. It was part of an ocean, and the word you're thinking of here is evaporite, if you want to go back to probably chapter 3, where we talked about rocks. The system opened, or the facility opened in 1999. As I said, it's supposed to hold transuranic waste, so both high emissions and low emitting waste, or contact handleable waste. And there have been several minor releases inside the system in the past, say, first 10 years. So in essence, no system is perfect, and we expect there to be fire or to be a release of material. Okay? The material is transported across the country. It's transported in big containers like this. It would be transported in, depending on the kind of radiation that's involved, in some kind of lead-lined container, which would keep, let's say, gamma rays from being emitted from the system. In some cases, there may be an inert gas or a liquid used to also as a barrier, a protective barrier. And it's transported on semis that have a GPS tracker. So, we wouldn't want someone to steal this stuff, and it would be very bad if this truck would get lost. So, in some cases, for remote handle, the storage is automated, right? So there's a place to install it. It comes down the tube, down, robots take it down, and machines convey it to the storage facility down here at the bottom of this set of essentially elevators, right? There is some thought about expanding this site to hold commercial waste. It's about a third full, so it's getting filled up pretty quickly in the last 10 to 15 years. But it isn't full yet, and we don't have any place to hold spent commercial fuel. Okay? The place we wanted to put spent commercial fuel was one of two. This is Yucca Mountain out here. These guys are all standing on a road that's right in front of it. It's an underground storage facility that has been constructed and researched extensively. It is notorious, in part because it was sort of politically a bullying of the senators in the region who sort of lost out in Congress. Congress voted to put it in Yucca Mountain and to research it. And there's quite a bit of money, okay, that's being paid into the system to research it by people who are generating nuclear waste, namely commercial reactor sites. Okay? Again, it's an underground system, and so the horizon where it would be buried to is right here. So this is a sort of a layer that would be hollowed out through drilling, and it would be in this zone protected from infiltrating or percolating groundwater. Okay? There are a number of reasons why the Yucca Mountain site was chosen. One is the rocks are fairly impermeable, okay? And although they are not perfectly impermeable, they also are being altered as water moves through them to what we call zeolite minerals. Now, zeolite minerals are silicate minerals that form in or from volcanic tuff or from volcanic ash. And that's what most of this rock here is. The other rock we looked at was an evaporite, so it was salt. This is volcanic tuff. And you'll notice the structure here. We see a kind of triangular shape for the silicate minerals. What a zeolite is, it's a ring or a chain or a cyclosilicate, and it has an open space. And in this case, the open space is holding on to cesium. Okay? And so zeolite is a kind of natural collector of anything that might get out of Yucca Mountain. And so this is why it is considered to be a good place. Other things that add to it, it has an arid climate, so there's not a lot of precipitation. The water table is way down here. It's very low, so the storage facility is right about here. Okay? geologically stable. So there are a bunch of faults in the region. Here's the Bow Ridge Fault, and then here's the Ghost Dance Fault. And faults are tricky because they work as conduits and barriers depending on how much fault gouge and the kinds of rocks that are present in the region. And you can't make a prediction as to what's going to happen. And so they've drilled into and explored the possibility of having these faults be transmitting fluids. And it turns out that some of them are transmitting fluids throughout the system. You'll notice here you have a perched water table that someone's identified, and then the main water table. And the perched water table is sitting on an impermeable layer right here. We wouldn't want any of this stuff to get out and into the aquifer system. And so there's a construction, okay, a construction mechanism or structure for holding on to the waste. Okay? The waste goes in these vaults, right? It's a kind of metal container or metal can. Okay? The waste is held in a kind of closed structure. This is our volcanic tuff. Okay? There's a stainless lining that goes all the way around the container, or at least in a semicircle around the container that's bolted into the rock. Okay? There's a drip shield over the rock, so that means if we have water coming in through, you can see all the fractures they've drawn in here, it's going to roll off and roll down. Okay, and so this is supposed to be a very sealed and protected system. And there's also, I think if I remember correctly, some element of the canisters in Yucca Mountain should have had like bentonite clay or something like that to help absorb water and lower the transmissivity, lower the permeability of the open space that's here. Yucca Mountain was stopped. The research on it was stopped. There was about $30 billion for research after spending, it was like $8 billion on researching this place, studying it, and now studying it for decades, right? It would have been studied in the region, would have been studied probably since 2001 or early, late 90s, or even early 90s. Probably would have been, research would have been going on to evaluate it. And it was only just a few years ago that I think it became too politicized, right? Because people live there, it's a low population region. Because people live there, it became a hot button issue for many people. Okay, all right. So Yucca Mountain is not going to open. It is one of two places that was designated by Congress. The other one, they never picked a site, but it would have been on the east side of the U.S. So we're going to have two sites to hold this stuff. So what do we do with radioactive waste? The only waste that goes to the WIPP site right now is military and Department of Energy reactor waste. Okay? Any kind of commercial waste generated, even if it's low grade, right? Low grade would be like materials exposed to radiation, but not actually an active source of radiation. High grade would be, say, for instance, spent fuel rods. Spent fuel rods are stored on site at nuclear reactors. They last, fuel rods last only 6 years, so pretty much every active site is going to have some spent fuel rod housed in a sealed reactor. Now, as the fuel rods age and are no longer suitable for driving a spontaneous reaction, they're housed inside. But eventually, they fill up the existing containers, and they have to be moved to external containers, usually that are held kind of in suspension of water or an inert gas to help deal with all the heat that they generate. We have, I think, 119 reactors in France. Shoot, I just forgot how many reactors we have. I think we have about 119 or so nuclear reactors in this country. So we have quite a few reactors generating power, and none of that waste has a place to go. We're just hanging on to it, right? The WIP site is the only site in the world that is active, right? An active repository for nuclear waste. All these other countries, Finland, Sweden, France, they're all doing the same thing. No one wants a site in their backyard. No one wants to have it close by, and so we're just hanging on to this stuff. Okay? All right, so that covers toxic waste, and sort of that's the end of our discussion of toxic waste.